All right. Welcome to my YouTube channel, guys. So we're doing the layout today of the BSPD main. So we switched some things. So the LEM sensor is no longer a separate PCB. It's all done in here now. Can I hide this? Philip made it go away. Yes, that sounds like it. Where am I? Nice. Okay. Is this gonna? So after you've made the schematic, you need to do the footprint assignment. I will not go through it here, but I have done it already. And then you want to start with your layout. So usually when you're doing the layout, the first step would be to see if you have any restrictions on the size or the shape. So go into NX or ask someone to help you go into NX and check if there's any dimensions that you need to follow. So yeah, you should CAD it first, then Olof will be very happy. But for this one, Tore has just told me make it very small. So we'll make it a square. We'll make it small to make it easy. Yeah, to make it easy on ourselves. But there's no angled connectors now.
You can defend this the connectors are also in the same.
But then we assume that they're angled for now then. And I'll change it later. Okay, so you press this. Oh yeah, I should say this. You need to open the .project file or underscore project or whatever, this one. First, then you can open the schematic and then you can go to this green button or whatever way you like to get to the PCB. Okay, so this is the current PCB, but we are starting over. So let's go into global deletions and clearboard. Yes. And this one I tried to remove yesterday as well. This one is not accessible, so I can't remove it, but it's just a marker. Okay, so in this view, I was thinking I'd first show around. So I'm going by mouse. So I recommend that you always change if you're using mouse or touchpad in the preferences slider. So I will use the mouse defaults. Then to quickly show around what things are here. So on the right side here, you can see your layers. So the layers are the different parts of the PCB. So if you look up PCB stack up, stack up, you can maybe see a good picture. Yes. So what is a PCB? You could first ask yourself. So a PCB is copper layers. And in between these copper layers, there's some isolating material. And what you do is you etch, which is like cutting with chemicals. You can cut out parts of the copper to create traces, like you can see here, which is then a electrical conductor, since this is made out of copper. And yeah, please stop me at any time if I'm saying something stupid. And then you have the layers, which are in copper here. So usually when we do PCBs, most are 2-layer, but we have some 4 and 6-layer boards as well. And these layers, the thickness can be chosen. So usually it's given in ounces or the thickness in actual millimeters. So ounces per square feet or something like that. Our PCBs are usually 1 ounce, and this all relates to the price in the end. The simpler the PCB, the less expensive, because it's the less harder to make it. That goes for like making super small holes, making things very close to each other, or having very thick copper. That all makes it more expensive. 1 ounce is usually enough for the PCBs you will be making. And yeah, so another thing there exists is these holes called vias. So as you can see here, what you do is you kind of drill a hole through the PCB and you fill it with copper. I don't know if that's the exact process. I think they probably do something a little bit different, but it's basically a copper filled hole so that current can go from one layer onto another, or not at all onto that layer, as you can see here. So that is just a way for us to connect to another layer. So when we do 2-layer PCBs, the purpose is because if we have a PCB here, what we have is usually some components on it. So you have some, maybe you have some, because this is pretty, yeah. You can, for example, have some kind of sensor here, and you have the LCD backlight. So to quickly explain it, so when we are doing routing, you will have to have some kind of input of power and ground, right? And what you want to do is you want one layer on your PCB. This varies so with how complex your PCB is, but in the beginning, what you want to do is just you create a layer on the front of the PCB here. Is just adding copper, you could say, a possibility to etch out this copper. And then on the backside of the PCB, so you have some prepeg or FR4, some isolated material in between, we add another layer. This is just so that we know that there is a layer there. This will make sense why I'm doing it like this. We're just saying that we have 2 layers here. So what we usually do is that the back layer we reserve for only ground. So the back layer is connected to the ground input of your PCB directly, and every single component that you place usually is grounded. But if they need ground, which is very, very common, what you do is you just route out a trace and then you do a via. And now you have a direct connection to the ground plane. And as we are not routing any traces on the backside of the PCB, we have a very low impedance ground. So why is this important? Well, you could, of course, for every component, give it power, like this, and ground, right? You could route it as a trace, just as we cut out copper here. So either you make this whole plane ground or you cut out trace. So why do we do it for the whole plane for the ground? Well, that is just for signal integrity purposes. So we've talked a lot about EMI. If you have a large shielded plane that can absorb EMI, but also think of these wires as having a impedance. So for there to be current going here down to the negative pole, you need a voltage drop, right? Because that's what Kirchhoff's law says. That applies for ground as well. So I'm going through this because it's not super intuitive if you don't think about it a lot, which all of you don't. Ground is not just a sinkhole for the negative parts or the receiving end of your battery, whatever you want to call it. U is equal to Ri or V is equal to Ri applies here as well. So we know there has to be voltages here. So if you have some very sensitive measurement, now I don't know if thermistor is the best example, but say you have some very sensitive measurement here, and suddenly you have this LCD backlight and you're routing the ground through it. Here you have your measurement, super nice. And then you have the sensor. Oh my God, sorry. Yeah, sensor and then some random R here. So if, for example, the LCD backlight and the sensor, if their return currents take the same path, well, this is a very power consuming component. If that's placed in the way of the sensor, then your ground here will actually be a bit larger than 0. And if your MCU is here and it's not in this path, then they might get different ground references, and all of a sudden your PCB looks 0.1 degrees hotter. I mean, it's not super important, but all these little things add up. And usually we do a ground plane, and it's partly because of that, partly because it's just everything pretty much needs ground. So if you have a ground layer, it makes everything easier. Then the front, we also make ground, but and that's also to make the routing easier, but it's not primarily for the current to go through the top plane. You usually want to add a lot of these vias so that your front and your back plane are extremely well connected, and these vias can carry quite relatively large current compared to the traces. Okay, so now we're going through a small bit of the background. So we go back into here. The front CU, that means front copper layer. If you hover over it, you can also see it. That was, yeah, what we were talking about earlier. You have the back copper layer. What else is important here? The front silk screen. So now, sorry for everyone on Zoom, but if you look at this one, the PCB I have in my hand, you can see that there's usually white text, for example, or around components, you could say like R21 in white. That is the silk screen. It's like paint printed on at the last step of the manufacturing, or one of the last steps. And when it says B here, it's back silk screen, front silk screen. And then you have the mask, which is what goes in between, like on the front layers, between the copper pads, for example, of your microcontroller. It's a very small place. And if you have mask in between, which is like some non-conductive, well, you could call it like some plastic in between, then it makes soldering easier, for example, because if you have some metal only in between, even though it's not the same net, or it's maybe just some floating metal, it's just copper in between, there's still a much higher risk that you short 2 pins. So by getting mask in between, you prevent that. And for us, that was really important on the slave PCBs, for example, where the distance between the legs of the MCU were so small that you could only make it in green for us to make sure that there was actually mask in between these legs. Yeah, it doesn't work out that way. And then you have, okay, user drawings. This is a layer if you, for example, want to add some kind of dimensions or something. This will not be sent to the, oh no, this is gonna pop up. This will not be sent to the company, for example, because in the end you're producing some files. You're not sending the KiCad to the factory, you're sending other files. Edge cuts, this is your board outline. And if you make any holes or shapes or whatever, it will be in the edge cuts. And the rest is pretty irrelevant for now. So how I like to start is if I have a shape. So say you have, it should be a 5 by 5 centimeter square, for example. Then I would usually start out making the shape first. So you can go in between layers here by clicking on them. You see how this blue arrow pops up? So I would first go into the edge cuts, and I would select either a rectangle or draw a line or whatever you want to do. And you can make then something that is 5, yeah, by something. So then you can make here the outline of your PCB. And now that I've done that, this is what it looks like. So there is this view button here. If you press it, you can go into 3D viewer. You'll see more of this, but this is a 3D copy of your PCB, what it will look like when it's produced, and it will include things like the silk screen. And if you have the step files for your components, which is usually in our libraries, you'll see them here as well. But we're not doing it that way. We said we should make it small. So the first step then for me is to import the footprints or the components. So on this button here, you can click it and you can click update PCB, and you will get all your components. Okay, so now I have these components here. Now you can see kind of how the footprint looks. So these red parts here is this on the front copper layer. These red parts are metal. So exposed metal on the front layers where you can route traces to. You can solder on them, do things like that. This gold, these are holes. These are the vias, but this is like a via for a component. So it's the pad of a component, a through-hole component. These you can also solder on. This blue thing, this is the silk screen. So you see how all the components have a name in this light blue. That's the silk screen. Okay, so what I usually like to do is I like to look at my components in the 3D viewer already now. Now you see I get an error because I didn't have a board outline. I removed this other one. So here you see the Lemo doesn't have a step file. This one doesn't have a step file, so they don't show up. But this DC shows up. This Wurf mini module shows up. So I can kind of see, okay, what's sticking out here. So J1, K2, J4, and VR1 are kind of bulky components. I have to think about where I place those. And the rest is smaller things that are not as important. So that means for me, I usually go about routing around the connectors, because usually your connectors needs to point in some way, or I think if you look in the rear LV box, you can see quite well how we try to align connectors to other PCBs and such. So I would usually start with just with those. So we said Tori wanted them to point in the out to the side. Now we can't really do that, but we can place them at the edges here. This will be changed, these connectors. So they should go to one on left side, one on right side, or both on the same side, or
Yeah, one to rear and one to front.
so I will just grab this space. We'll do like this. So we'll have this one is gonna point to the rear, this one is gonna point to the front. So okay.
The car.
Yeah. And for me, this is the front of the car, this is the rear of the car, because we are on the front copper, right? And I'm thinking that it's placed on the right wall now. Should it be placed on the left wall, maybe? Okay, then it's right wall. Perfect. So we said we wanted to make this PCB small. Well, there are several ways to start. You see these white lines? These white lines are indicating what should be connected where. So you can remove them if you want, but it's showing you what items are linked together. So these give you some idea. You see that there's a lot of interconnecting lines here. So these give you some idea that this component should probably be pretty close to make the routing of the traces easier. And now that we're saying, okay, we're making a small PCB, I have a trick that I like to do. So in the PCB, you usually have grouped your functions in different places, in different blocks. So for example, here I have grouped the power into one block. So then it would make sense that all of these are close to each other. And usually, like if you have some component, like an op-amp or an MCU or something, it has a power supply. So this is the power part of U1. Okay, it's the NOR gate here. This is the power of the NOR gate. Then I know that C1, for example, it should be close to the OR gate. But we'll go through that later. We go back in the power block. These all should be close to each other, and there's a reason why we have the capacitor here. It should be close to the output of this DC-DC. Usually put the capacitors close to things that are emitting disturbances. So this is a DC-DC, a switching regulator, power supply regulator. It will produce noise on the output. So by having these capacitors very close to the output, we make sure that we filter out this noise before it reaches any other components. And same for the MCU, it produces a lot of noise because it has clocks, it has a lot of switching things that all produces noise. So we want the capacitors close to it. Yes, so what I like to do, I just highlight all of this, even the text, because the only things that are in here, now they're linked. So now you see that all of these are highlighted. So boom, now I have all these power blocks separated, and I know I want to keep them together. So I will just grab a corner up here and I'll put them there. Now I will go back and I will grab this thing, the LEM sensor. Okay. I now know that these all should be close because you have made a function of your PCB, so you should know what kind of relates to each other. So these all things group together, I'll put them down here. And then what did I not select? I didn't select this. This is because they relate to some connector, I think, if I remember correctly. Yes, they relate to this one, so I will put them here. And this will make sense very shortly why I do it. Signal conditioning, these are related to each other. So we take this and we put it here. And then we go into the next one. Do we do this one? No. Make sure you get this as well. So, okay, for this one, maybe it's a bit harder. I would actually split up into two. So maybe we do like this. Yeah, let's do like this for now. It's not super important. It's just to make it easier for you. And we said that this was U1. Okay, so U1 is this one. So we want to make sure that we get the capacitor with this as well. So we take this, place it here, and now it should be very shortly done. What do we have left here? We have this, and we have this. I don't know if that's selected. Okay, now it's selected anyways. Perfect. I pull them down here. Now, final one is the relay, so the shutdown circuit. And we take this, should be close to each other. Perfect, they already are. Okay, so either you can start, as I said, if you had the board, you could already now add layers, but I will not do it. I will show you first what I'm doing. So ground, don't worry about ground at all now. That will solve itself with the layers. So the first thing I'm thinking is, okay, how can I make this tight? And I know this component, you see this this blue part here, it outlines the size of the component, and this white line is the front courtyard. See kind of how it disappears when I click. So that indicates like where the edge of the component is. So I cannot overlap these white lines. You see how it gives me a red as soon as I do it? That's because now I have two components touching each other. So I can't put it this close. Instead, I will go ahead and put it up here because I see, okay, there's gonna be a connection here. Let's put it here. So this will be a bit tedious. You'll have to follow with me. And what I'm doing now as well is I'm looking at the function a bit. So I already know that since I designed this is a relay. Relays have a coil in them that is, when you drive a current through it, it's generating a magnetic field. This magnetic field accumulates energy. And when you want to open this air again, or this relay, sorry, you want to collapse this magnetic field, but you have to get rid of this energy somehow. So we have this flyback circuit here. So I know that these two should be pretty close to the relay supply here, so that we don't generate noise. If they're like way off and it has to go through the ground plane, then I'm generating noise. So I'm putting it as close as possible. So I see R16 should be here as well. Nope. And I can even, sorry. Okay. And we put, and I'm pressing R to rotate the component. And I'm placing it here. Okay, this is looking pretty good. And let's continue. I don't know if I should do, I don't think I can do the whole thing now. So we'll do a part of it on this tutorial. So let's just see what we can do here to try to make this small. Just playing around with placing things. These numbers or reference designators, I think they're called, are primarily here on the silk screen to help you when soldering. So if you see that D16 is this one, I should place it close. Try to keep them if you can, but don't make your PCB larger because I need to, for example, have this D13 in between here. Like this. This is really stupid. Then just move it out of the way. And if you're making something really, really small, they might just be super annoying to you and don't fit. Like they just take a bunch of extra space. Then get rid of them completely. You can, I'll show you a trick. If you want to select multiple things, you can like do like that. You see how I just selected everything. And then if you right click, you get to this window, select. Then you can go to filter selected items. And here you can select to only get certain things that you want to get rid of. So for example, I could select only the footprints. And then now only my footprints are selected, nothing else. Now I only have footprints. So and there's also in the edit file here, you can change you can delete all your tracks, all your vias, or all your text or stuff like that. You can also edit every track or every via on your PCB, for example. So these are all things you can do. But let's just group these relay things up. So, okay, this is decently small. I'm okay, happy with this. So if you have grouped things pretty decently, let's assume I did a bit more thorough of a job. Then before you can do anything else, what you should do is head into the, if you're using GLPCB or NCAB, you should head into their respective design guidelines or design rules. So these are not always super easy to understand. I don't have the NCAB one right here, but what you need to do before you can start routing or anything is that when you order the PCB, I will show you how that looks. So when you're going to order the PCB, you're going to upload your files here. And sorry, let me just take something. Maybe this one has something. Sorry, I know I did this. The PCB order. Maybe like this. If I upload the EBS, for example, yeah, I get faced with a bunch of options, how many layers I'm doing, what the dimensions of the PCB are, how many I want, and it's also gonna ask me for the thickness of the PCB, the copper weights, and well, many things. But some things you have already specified, like the sizes of holes where things are placed, and they cannot make like anything. So you should follow these guidelines, and you should, if there's a, like we are doing a rigid PCB, not a flex, you should always try to be like a bit on the safe side of these capabilities, because the safer you are, usually it's more cheap, and also the risk of a manufacturing error occurring is less. And if you're ordering from like NCAB, they will help you with this, and they will not send out anything to manufacturing. That is wrong. But from like yield PCB, there's a larger risk that you're running into an error where a via is somehow connected to power and your board is just shorting, and it's very hard to find. Sorry? They do. Yeah, yeah. They should test it. I think it's quite a lot. I checked a bit in between NCAB and GLPCB, but the issue is it's like it looks pretty clear cut when you only look at one of them, but when you look at the others, it's usually quite hard to see what's what. Because what we're doing now is we're going into the settings of the PCB. So there's this board and there's this settings wheel. Hello? Oh, my computer does not like this. Yes. So here you can decide, for example, how many copper layers you want. So you see I can do all the way up to 32 layers. We're running with 2 on this one. You can do the thickness here. So this is 1 ounce thickness. And if you're doing more or what should I say, like 2 ounce, 3 ounce, yeah, you can adjust these values. It's more, I don't think this actually sets the thickness. I think the thickness is set by what you choose when you manufacture it, but this is good for someone looking at your PCB because you may have dimensioned your traces for a certain copper thickness. So if you reorder the PCB and you don't look and you haven't changed this, and it should have been a 2 ounce board and you ordered this as a 1 ounce board, it can burn out. So important to check. What else is important here? Design rule. So the program will not let you break any of the design rules, and this is very good for you because it means that when we have set up everything according to this website, we are sure that when we try to do routing and things like that, we will not break it, so we don't have to manually check everywhere. And it also makes it so that when we run the design rule checker, which I will show you later, you will get warnings or errors if you have exceeded any of these setup limitations. I should also show you, if you haven't, you should run the ERC before you, after you've done the assignment, or maybe even before, and see that you have not made any mistakes here. So we'll see, yeah, I have 0 errors, but I have some warnings. So you should check through all of this. So here it can say like, what could it be? Yeah, symbol therapy not found in symbol library device. This is because I updated KiCad. This is an old made with KiCad 6. I'm now in KiCad 7. I think here is like brake pressure supply is just 24 volts. So it will call it 24 volts. It will not call this like brake pressure supply. It doesn't matter to me. So all these warnings are, I don't care. No errors. That's okay for me. So going back into here. Now it's trying to set this up, and this is not super easy. So I will see what I can do here. Maybe we should do like so. So the first thing they asked for, right, was the minimum clearance. And a tip, if you click in this box, you can get the description, right? You hover here. The minimum clearance between copper items which do not belong to the same net. So, okay, where do you find that? Now you have to start the scrolling. So it should be minimum clearance, maybe. So pad-to-pad clearance 0.127. I don't think pad-to-track 0.2. So the smallest one is 0.127. So that's what I'm gonna use, and I already pre-did it. Sorry. So the minimum clearance will be 0.27. Minimum track width. So let's go into track, see if we can find it. So minimum trace width. Yeah, and here you can also see the spacing. So we're doing 1 to 2 layers. Minimum trace width. Here they also give you like an explanation. So you see how this one is minimum trace width, 0.127. Now we should also add when it comes to trace width. So this is like extremely tiny. Even a 1 amp current, like if you do 0.17, you might just burn this trace up. And this no one will ever warn you about because they cannot know how much current will go through your traces. So, but we'll come back to this a little bit later. For now, yeah, 5 mil, that's just American measurements. I think there's something like, it all looks very nice. If you use mil, everything is even numbers for some reason. But yeah, millimeters is fine. You can select if you have mils for some reason, you can go into the preferences or somewhere and you can change it. You can Google it as well. But I will do minimum track with 0.2 because, I mean, I don't need to do it 0.127. I don't know why you would do that. 0.2 is like I advise you not to do smaller than that. And as I said, you might order from another PCB manufacturer later, and you might have issues if you like go to the absolute limit. So try to be a little bit above. Maybe even here we should do something like this just to be clear. Minimum connection width, I think you can leave that at 0. Tore, do you have any minimum copper width of connected copper items? I think that doesn't matter.
At 0, you can.
Yeah, it was at 0. I think like if you have a very small trace connecting to some pad and you want to limit that, you have to make some kind of special way. You can. I don't think it really matters. Minimum annular width. Yes. So oh no, they actually show it. So annular width is like the outside of the via. If I can find a good picture. Yeah. The annual width is from the inside of the hole to the outside of the copper here. This is the annual width. And we can see if we can find it. Minimum annular ring. Nice. Yeah, here's it as well. 1 ounce copper, right? We're using 1 ounce. It's 0.13, but I will be on the safe side and I will do 0.2. It's okay. So 0.2. Minimum via diameter. Diameter is the whole length across. I saw it up here, I think. Via diameter. 1 and 2 layer PCB, 0.3 millimeter hole size / 0.5 millimeter diameter. So I will set it to 0.6. Copper to hole clearance. See if we can find it here. Drill hole sizes. No. Board outlines. Copper to board. That will probably be mentioned later. What do you say? Hole to edge. Hole to board edge, more than 1 millimeter. Now it's 3 for some reason. May have been that I checked NCAB and found that they had a larger one. So we'll leave it at that hole to edge of 3 millimeters. Yes, what else do we have? Holes, minimum through hole. This is the drill size. And hole to hole clearance. You can find this. I've already done it, but you just scroll through. Micro bias we don't use. Silk screen, yeah. You can exceed this. So the silk screen is like the final layer where they print it on. The only danger is that your text is going to be unreadable if you do it too small. Just do what they recommend. They say it here as well. I think they call it legend here. Yes, legend. They specify width, height, ratio, set it up, but don't be afraid to go a little bit smaller. It may be a little bit unclear what it's saying, but I haven't had any issues. And NCAB is usually very good at you can go very small. Then you have this as well, minimal thermal relief spoke count. So thermal reliefs are to make the connection to the copper worse, to aid like soldering. So you don't have to, if this pad is connected to copper or a ground, you would have to heat up the whole ground layer to make it, because the thermal conductivity is so high, you would have to heat up the whole ground plane. It should take a very, very long time to get the good connection when you solder. You use these thermal reliefs to aid the soldering process. Any other explanation or way to say it? No. Good. Okay, so the board constraints is set up. Predefined sizes. Yeah. So our tracks, these are the like cables you're routing, traces. We said 0.2 in the design rules, so we should not go under 0.2 here. But what you should always do, if you have like an OR gate or it was okay. If you have things like that, it's usually very low current. Same with your MCU, it's low current. But if you have some kind of relay, that may consume a bit more, or you have like an LCD screen, what else? Shutdown circuit, yeah, things like that. You might have 1 amp almost of current running. And what is really important here is two things. Now I will mention it because it's easy to make the mistake. The resistors we use, for example, are so small that you should check always, like an 0603 resistor can never handle more than 0.2 or 0.25 watts, I don't remember. But you need to check that your components, if you're doing a current division, is not consuming more than that. Think about that for flyback diodes as well. And then for, say we have our shutdown circuit. Currently it's fused at 3 amps. So you don't want your PCB to burn, you want the fuse to burn. So then you would have to dimension all your shutdown circuit traces to be for 3 amps. I'll just show you what that would look like here. So if we do, you can usually use your PCB trace with calculator. KiCad has a built-in tool. You can find that one yourself. I usually just use this one. You can also, in KiCad, you can also calculate current in that one. But yeah, say you're doing 3 amps. Here's the ounces. We said we had a 1 ounce board. Here, put something like this. Don't let it go above 50, start at 20. The temperature doesn't matter extremely much. We want it in millimeter. Then for an external layer, we would have to use 0.9 millimeter wide traces. That's a lot more than the minimum 0.2 required from. Yeah. Yeah, if you go. Yes. Thank you. Yes. If I up it.
Ambient temperature is high.
Yes. It's actually not increasing the. Aha, sorry. So yeah, it does do something, right? Only the resistance. Yes, because in these compartments, for example, for the high voltage PCB, we did 50, but I think if you're gonna be correct, the cells can go up to 60 degrees. And if the cell tabs are 60 degrees, my logic is you probably have almost 50 degrees in ambient temperature in the worst case in the battery, right? Yeah, but that I was like, okay, this is the worst case. That is okay. So what we said was 35 because in the rules everything has to be rated for at least 85 degrees. That is in the TS system. So my thinking was like, okay, to make it compatible with the environment, this is what we should do. Maybe we can discuss if this was the right way or not. We will do it in our report. So if you want to learn a shit ton more about PCB layout and designing and stuff, you can read that one when it's done. I hope it. Yeah, I mean it should be good. It's me, Francesco, and Ian, and some other guys, and we're spending like 2 masterpieces doing the work, so it should actually be good. We'll see if it's possible to read it after the. Yeah, I should not say more. But for the shutdown circuit, I think we should dimension it for 1 amp, and we'll adjust the fuse accordingly in Dev 18. So we see here required trace width 0.365. So then for me, I will use the 0.41. And then I will use the 0.2 everywhere else. And these usually aren't here. This is just, I don't know why they are already pre here. When you get it, it will look differently. So I have these two traces I will use. So shutdown circuit, this one, else this one. And bias, you need to make sure that these comply with the design rules that you selected. So I know this one should be all right. So I'll keep it. Yeah. Yes, exactly. And I think if you want to check already now that none of your, yeah. So if I just start placing vias now, you might think, okay, it's gonna be cool. I selected the right size. No, you didn't. You have to go up here, and you have to actually select what you're using. And this little equal here, I'll show it later. If we just want to check if our via is okay, I just place one, and then I run the DRC here, and we see, yes, it did not give us an error, so it was not too small. Now it gave us 1 million errors, but that's because, yeah, we didn't do the board yet. So I'll delete all of this. Yes. Okay. So for this not to take too long, I will focus on this part only now. So it has shutdown circuits, so it will be relevant. So the first thing we'll design this. Yeah. So the first thing we want to do is now, for me at least, I like to route components like this block by itself, and then this block by itself, this block by itself, and try to make it really, really small. There are certainly other strategies, and when you're routing, don't be afraid. So at this point now, save, push to GitHub and write where you are at, and then just go crazy. Try things out. If you're not happy, start over. Like in this stage, you can't do wrong, or you can do wrong, but the layout usually takes a few attempts. You have to like think about where you should place components. When you place everything, you might realize, oh, this didn't really work out that well in the end. So don't be afraid to do over and try. Do you have any strategies, Tore, when you do layouts?
Try something.
Yeah.
Try again, and then
I don't know. Okay, Tore.
No, I wasn't saying.
Oh.
It's a process, and you learn by doing. So don't be afraid to start somewhere. Forgot about the signal that you can't route in a good way without like routing it around the entire board with the 5 million data, where just aren't satisfied and then you decide to think it's probably.
Yeah, or like for me yesterday, I redid a PCB and I tried to make it smaller, and it wasn't really that much smaller. So I realized I had to do some other strategy to make it smaller. But
which one are the signals that should be are there any signals that should be? Yeah, exactly. You should try to prioritize your signal. Try to prioritize your signals. So route the important or sensitive signals first, and also noisy signals should stay away from sensitive signals. So yeah, try to prioritize your signals, of course, and try to place noisy components that are not that sensitive in one area and place sensitive components in another area. For the BSPD, for example, the relay should probably be far away from the analog front end. And that's one example of placement.
But it's good to do this kind of like I started with placing everything in one block. It's one way to do it, but like now I placed all of this in one end. I know this all belongs together. This needs to be close. And then I can take this block and place it far away. And this DC-DC, for example, will be noisy. They can be pretty close together probably. But then the analog stuff, as Tori said, this stuff, I can place it in the other side of the PCB here. Okay, but I like to route locally here actually, because then I can easily spot issues. So you see how I try to rotate everything so that these white lines go pretty straight and pretty short. So I've selected 0.2 here, and then what you do, you have the router here. And anytime you see this black thing, that means you can like hold down and pull out to the side and you get up more tools. For the router in the beginning, you're just gonna use this one. You either click here and you get the router, or you can hover over a pad and you press X. And now you see things got highlighted. That's where this trace should go. So you see how I'm trying here to go onto the 5-volt pad, and I can't. Here's where it comes in. This this is not really a rule. This is built in for every PCB, but see how you can't do things like this. But if I route this pad, it'll automatically like snap into place. So I just start routing, and now they're connected. You see the white lines disappear, and I try to route it, and I don't do the ground, and I'll show that later. So now I route this up, and yeah, we'll do something like so. Wait, you know what? I can actually speed run this probably. So we go up into here, and now, oh yeah, I should show you this as well. And if we'll do it like this then. So things not to do. Now it's a bit unintuitive, so I will do this. If you have a trace coming up like this, and you want to connect it here, what you should do is always keep 45-degree angles. Or not 45, but keep it non-90 degrees. So if I go like this and I do this, this is bad. This is kind of unintuitive because it looks nice. But the reason is because the trace width here is not consistent. Here it will be a little bit longer than here, or wider. And that isn't a huge deal in most signals, but like all the small little things you like all the small little rules you follow limits the noise in your circuit and the faults that may occur. And when you're routing more sensitive, more advanced stuff later, this is second nature to you. You know, when you, as soon as you see this this 90-degree angle, you know this is not good. So how can you fix it? Either you just delete and you route again and you try to make it 45 degrees, like, okay, then like, okay, even, yeah, you get what I'm saying. Or there's another way. So in KiCad, there's two things you can do. You can either highlight something and then press the M, or right click and press M or move. Then you can move things around, and the electrical connection doesn't keep itself. But if I, for example, click and I drag now instead, then the electrical connection will remain. So you see how I can do this. So this is just a tip. So that's way faster than deleting and rerouting. You can just pull on things like this. What? And then, yeah. And here, yeah, I just said the no 45 or 90-degree. Yeah. Yes. Oh, bad for etching as well. I did not mention that. So etching is, as I said, chemical cutting. Like you put chemicals to remove the copper, I think you remove. What they do is that they have a
piece of glass fiber.
I don't think you hear if you're not in
Piece
front
of
of
glass fiber covered in copper on both sides, and then you apply a photoresist, which is just a coating of material that is sensitive to light. Then you put on like a lamp template that looks like your circuit, and shine on the copper, and the copper that is not masked will be hit by the light, so the photoresist will disappear more or less. And then you put it in a etching bath, which etches away the copper that is not covered by the photoresist anymore. So it chemically removes the copper that was exposed to the light. And this is a very inaccurate process, I guess, more or less, and that's why they can't guarantee this case touch, and that's also why you want to have filled copper layer on all parts, because you want to remove as little copper as possible, because then you can keep your PCB in the back as short as possible, which is good, because otherwise you risk catching away the rhythm and stuff.
Now I will add something that we learned as well. If you have open edges, you might get, what's that when you get bow and the bending, or they said something like that as well?
If you have
Oh,
copper on one side instead of the other, so it like across the whole layers, it should be as symmetric as possible. Otherwise, if one layer that is like the inner layers is thicker, but the other one then here in the edge, I guess it can bend the whole structure.
yeah. All right. Now we learned that as well. So I will just do it for this one because otherwise I think we're running out of time here. So we'll do the edge cut and we'll do a square. You see how I selected the edge cut layer. Now we have the outline of the PCB. So if you look at it, we have our PCB here with our components and the rest is floating in the air. Now you need to create these copper layers. So if I press here, I select the front copper layer and I select add a filled stone. Now I just select the area. You can select a very large one. It doesn't matter. And as soon as I clicked here, I got this option. Now I can make this copper a net. So we want it to be ground, right? So I select ground. Now this one is in the way. And you can, if you have some settings you want to add, you can do it here. I think this is okay. You press OK. You make the outline like so. And then what you do is you press B. And that builds or fills the zone. So now we have been in this mode all the time. But if I press here you can see all the copper. So all this red is copper. And you can see here, because of our ERC rules, that the copper is not filled all the way out to the edge. Because this is what we specify the copper to edge distance. And I can switch between seeing the red and not. And if I'm in this mode, then I can press Control B, which is like unfill zones, can remove the copper. Let's just see how it's built. And then of course we want to do it for the back layer. So I press this one and I go here and I just select ground. Okay. And I just do something, yeah, like so. Shape doesn't matter as long as it's around this one. So now when I press B, hello. Now when I press B, we have the green stones. So I can flip between them by doing this. And now I think already you can see in the 3D viewer that it turned light green. So you can see here the dark green, that's no copper. Here behind the light green, there is copper. And around here, this is the firmware release. You can see how the copper is only here and not in these zones here to aid soldering, because you have a less thermal conductive. Yeah, of course you have less electroconductive path, but you have also less thermal conductive path, and this should be enough electroconductive path, I think is the point. And when you route traces, I think they add more copper, but I'm not sure about that one. Yes, now we have done that. I'll go back into this mode. So now let's just assume that there is, now I just have to pretend here a little bit. There is a trace running here, okay? This trace is between some components. And now I want to route this to shutdown circuit in. So I can't go around this trace, right? Okay, I can, but I can't go around it. So what are my possibilities? Well, here in this case, it's actually okay to route on the back plane. So you want to reduce the amount of traces on the back plane. Like I can, whenever press here on the back copper layer, and I can start routing from the back copper. And then you see how I can just go straight through it. But what happens if I have a bunch of wires on the back layer here? Well, suddenly, in this case, for example, if I have ground here and I have a ground component here, what happens with the current? I have to think always, this part is gonna be some net, maybe 5 volts. So this isn't ground. And okay, sorry, I have to. Yeah, now if we go on the back here, you can see that no current can suddenly go here, and not even here in the bottom, because there's no copper here. So the only way a current can go from here to here in ground is if it goes like so. So you see here we have this very, very small pinch point. This point will have very, very high resistance because it's going to be quite a lot of current going through here then. So there might be quite a substantial voltage drop. And this is where you create issues. That's why I want to limit these traces. And if you find that your PCB is so constrained because it has to be small that you can't reduce the size of these big traces, you can add more layers, which I will show you. But so if I want to route here, I go into the front copper layer, and what you can do then is you press V. V automatically gives you a via. So I go very close and I try to be perpendicular to the trace below here. And now I'm going on the backside and I press V again, and I try to like this. So you see how I now went under the trace. Here is also important to be perpendicular. Why? If you have read the TET course, you can see that if this one has we have 5 volts here and we have ground on this trace. What is this? You see it? This is a capacitor, right? This is what a capacitor is. It's like 2 metal planes with something in between them with different charge. So there will be a capacitive coupling between everything that you route that is close to each other. So here these two will have some capacitance in between them. Of course, this is very, very small, but the more sensitive signals you start to work with, I mean, the more important these things gets. So the habit of trying to keep perpendicular traces like this is very, very good. And even for, you may have even heard of it, there's something called impedance matching. So for some, the impedance in the traces is so important that the traces even have to be the exact same length. So here you can have like tools for routing a differential pair and trying to create different impedances in these traces. So if you're doing something, some analog radio transmitter or something, they are usually very sensitive to these impedances even in the traces. So yeah, always try to adhere to the rules that I tell you, even though it probably won't affect this shutdown circuit signal. And yeah, we also said that shutdown circuit, right? It should actually be 0.4. Oh, it was 0.4. Good. Yeah. Okay, so what does it look like if you want to do more? I will just show you this as a bit of extra. What if you want to do, more layers because you're just realizing it's a bit tight, your routing? Well, for this one, I did 4 layers. So I have the two, and this PCB is also part of the new Becky, where this PCB sits kind of as a server rack thing. It means that it's not lying on the bottom against some box. So I can actually place things on the back here if I want to. But here you can see I have quite a lot of traces on the backside and they're pretty long. So this is not what you should do, right? But I have 4 layers. So here you can see front copper, internal layer 1, internal layer 2, and back copper. So my internal layer 1, which you can I can select here, is ground, and my internal layer 2 is, hello, is 3.3. So I have a completely unobstructed ground plane. If I show you how it looks like, don't mind this. This is for another reason, but there are no like breakages, like no traces in the ground plane. So it's a really good ground plane, and I also have a complete 3.3 volt plane. So most of my components are, or a lot of them are connected to, most are connected to ground, and a lot are connected to 3.3 volts. So I set 2 planes like this, so I can at any point just drag out a trace and then do a via. So you see, this is not connected to 3.3 volts now. It wants me to connect to 3.3 volt. And if I do X, so start writing track, and I do via, this just connects this via to only the 3.3 volt layer. So that's pretty cool. I don't know if it shows you. Okay. Well, it doesn't really matter. But yeah, that makes it easier for me. I don't. There we go. And then I can route as much as I want on the backside. And here you can see that it was kind of tight because there's so many signals going everywhere on this PCB that I had to make it a 4A board to fit. The other option would be to make the PCB larger, but I also wanted things on the backside because the backside is now visible. So here I use the backside as kind of the debugging part. It's not super clean. This you could have put in more components on the back, but I have some indicators for the shutdown circuit, which we usually we want to see when we debug. So this would be very, very visible and easy to see for you. And I also here like played around a bit with the silk screen. So I know this is a point where you usually probe. The component sticks out the other way. So I know the legs of these relays will be here. So I can physically probe without looking in the schematic what leg is what here and see if the shutdown circuit, or if the shutdown circuit is actually closed here or not. Like this is just extra things. And I can show you here as well. So another part of doing, I think, decent silk screen, here you can decide if you want 5 volts or 24 volts as the PWM cooling supply. So here I write like 25 volts and 5 volts and 24 volts, and I write what you can actually do with these jumpers so that you don't accidentally look here in the PCB and try to find out what this is doing. It's very intuitive in a way, what you should do. All of these little things help, like naming the LEDs here. These are all diodes. Their names. This is the power from this shows that we have power in the board. It's named. And then, yeah, I just add that, yeah, this connector, where does it go? This is SPI. Okay, then I know what it is. And then, yeah, the relay is what they do. And then, of course, what PCB it is, who created it, and you can also Google how to make your own logo, and you can import it. So this is my logo, this is this logo, and the KiCad for my student logo as well. And what's important in this, when you're doing the placement of things, so I'll go back to the other one. So if I take, now I'll just show you this one as well. This was an error that was on a lot of our old PCBs for TV16. This is the DC-DC. If we look in the 3D viewer, it's kind of a large component, right? Sticks up a bit. And then if we have some connector, for example, an MPC4 angled connector, and we place it, you see this blue? If I cross in here, you see this blue? This is where the the outline of this component is. So this component fits here, right? This is no issue. The blue lines here aren't intersecting, so we know that the components aren't intersecting. But we look in the 3D viewer now. What do you see here? This connector, it fits, but how will you ever get the male plug of this connector into this point? It's not possible. If you don't pay attention, you might do these mistakes. So use this 3D viewer. It's easy, like these Burt mini models, for example, the cable goes out to one side usually. Don't put this next to a wall and have the cable come out straight to it. Like, think about the physical dimensions, how you're gonna plug everything in. And as you get more used to PCB layout, this will be very intuitive for you. But in the beginning, make sure you don't do any mistakes like this. And this is also why we look at each other's boards to find things like this that you may be blind to otherwise. Yeah, naming wise, I should say it. It's very easy to, if you want to write something on the silk screen, that you just press this text thing. But what you need to do, and then you write something, but then it goes in the copper layer. So you should actually always make sure you select silk screen. And then when it comes to naming of things, stick to the GitHub name. So you usually write, for example, this is PSPD main, it's called in GitHub. And then, yeah. And then what should also be mentioned is who made this PCB. I think that it's nice. For example, Jordi made the design, the schematic design. So what I usually do is I write that Jordi is the system creator because he did most of the work here. And then I write that it's updated me and Filippo, and what date and the car number and what revision. So this is the next revision, it's 1.1. It's still mostly Jordi's PCB, so I give him credit, and I think you should do the same. It's just nice. So when I do the PCB, I'm gonna write Jordi, and I'm gonna write myself as well and Filippo, because we all did this together. So, I mean, this is up to you, but I think it's nice to credit the people who put down a lot of work into these PCBs that you might be working with in the future. So, I mean, if you do massive changes and system is not really what it was, put your own name. But yeah, think about crediting the alumni. We really value their experience and their expertise. So they'll be very happy if they see that we think of them and that we appreciate them. Tore, do you want to mention anything?
No.
Yeah.
Ask if useful and also for the image. And they plan to try new things and what do you say? Criticize or give feedback. Because of this to get the good design. So just play around and try it. Like, you can always redo. And yes, in the other tutorial I did, you can watch that one as well. I also go through like the design rule checker because we got some errors when I did it last time, and how to like go through and check and fix them. But I will not show it today. Yes, quickly I should mention this all. So this little equal here, it's just a tool. It will make sure that even if I've selected 0.25 here, this trace is 0.4. If I start routing from here, it will keep the original trace. Sometimes that's nice, sometimes that's annoying. It's one of those things. Here, this one as well. You can either have, okay. My mouse doesn't want to do it now. Hello?
Okay, usually you have like a crosshair of your mouse, and your mouse doesn't look like this, so I don't know what's happening, but yeah. Yeah, here you can change if you use mils or millimeters. Yes, this is just to highlight the copper on the current layer that you're out. So here you only see the copper on the front layer, for example. Yeah, I think that's it. Another nice thing. Yeah. Oh, I have some small more tips. If you have done some very long trace and such, you can right click a trace and there's unroute selected and removes all the complete trace. Instead, if you do something like this, it creates 2 units. If I press the track, I press delete, it just deletes that small part, and then I delete this, and then say, oh, it was this little thing. So it was actually three units. If I right click and I press unroute the whole thing. Sometimes also, if you're doing some fancy PCBs, you may want to, yeah, if you press E, you can see all the settings you have for your PCB or your components or whatever, your trace. You can also orient it at a 45-degree angle, for example, if you want. Be a little bit, you can just do this wherever, but sometimes this may be the difference between a really nice looking and small PCB and a very bulky one, so use it. And the last thing, so you have components or connectors is usually more important, and you want to place them. Oh yeah. Okay, so you have a grid on your, which is like where your mouse moves. So now it looks very smooth because I have a very fine grid. But if I go up here to a large grid, oh no, it doesn't work because my mouse is not. Oh no, they deleted everything, right? Okay, well, okay, my mouse doesn't work. That was unfortunate. It's probably because I'm in the Zoom meeting. Okay, but yeah, usually if you do like 25mm square, you will feel how your mouse is skipping a lot. I don't have any commands. It usually works with just your mouse. Skips the whole thing. Or maybe it can see the components. Yeah, here you can see the big skip. The component is jumping a lot. So pick a grid. Pick something like 0.1. It's usually okay, and stick to it. Don't change because then your components will be impossible to align. But if you need to align components, like say C12 and C10 here, if you have 2 connectors, it's usually more important. If I want to align this one with this one, you can right click or you can press Shift P. Then you go into this positioning tool and then position relative to. And then you can select item. So I want to have it positioned like 2mm above C12. Then I press in the middle. If you accidentally press on the pad, it will only select the pad. So make sure you select the middle here, and it says item reference footprint C12. And then in the Y direction, I want it to be 3mm above. I press OK. Okay, it's below because it's looking at, yeah, I don't know. Well, it doesn't really matter. I don't know how the X and Y axis is set up here, but yeah, it's a very good way to get them perfectly aligned. And I use this a lot for connectors and such. And yeah, for now, I think that is, no, yeah, if you want to connect the component, or you want to put components on the backside, you can press F, flipboard side, or you can right click again and go to change flip side. And if you're doing a lot of routing on the backside or component placements or such, there's this view and you can press flipboard view. And now this is how it looks from the backside. This can be pretty useful. That's it, I think. Any questions? Yeah, good. then I will upload this on YouTube, and then you can watch the other 2 tutorials, which is basically on the same PCB, but there I'm sitting at home and I'm going at a bit more of a fast pace. So that one might be good to check to remind yourself before you start your layout again, just to get, then you heard it twice. And I don't know which one is better. You will have to judge. It's like the other one is like 1.5 hours, so this one is maybe longer, I don't know. But yeah, thank you for watching. Like and subscribe, yes.